Hello and welcome to another edition of Hariba Raman Academy. In this installment we'll discuss Raman spectroscopy and specifically micro Raman spectroscopy as we apply it to molecular electronic materials. And in particular we're going to see the effects of orientation and crystallinity in these molecular or organic electronic materials manifest in the Raman spectra. This is just a short talk and we will cover just these topics. First, an introduction or reintroduction, I'm sure to many of you, of the field effect transistor, and specifically the spatial scale of integrated molecular electronics, which is large relative to that for the silicon-based or gallium arsenide-based integrated electronics, and therefore makes it suitable for optical microscopy and optical microspectroscopy. And then give you an example with Rubrene, which is a material along with pentacene that are commonly used these days by many scientists to try to fabricate integrated electronic circuitry with organic compounds. So here's a diagram of the field effect transistor, and so what we see is the familiar structure. We have a source, a drain, a gate. What's different in the case of an organic semiconductor is that we're essentially replacing silicon which is ordinarily doped with N or P-type dopants with an organic semiconductor, and generally speaking it's crystalline. Today we'll discuss the results of micro Raman spectroscopy of rubrene grains taken right out of the reagent bottle. And so why are we interested in molecular electronics or integrated electronics based on organic compounds? Well, it is definitely not to replace silicon-based integrated electronics and chips and that sort of thing. Principally, it's to apply integrated electronics on display and displays on substrates that are flexible, and for applications where the rigidity of the conventional semiconductor substrates would just preclude that particular application. All right, well, one of the compounds that I mentioned that's frequently used is rubrene, and in this diagram that you see here, it's rather helpful that the authors in their sketch or their diagram show a rubrene crystal as the active medium in their transistor. Now, why do I say that? Well, that's because the important characteristics such as electron and hole mobilities are highly dependent upon the solid state structure. And it turns out that those electron and hole mobilities are highest in crystalline materials, and not just polycrystalline, but single crystalline materials, and along specific crystalline axes. And this is where the polarization and orientation sensitivity of Raman spectroscopy comes into play. All right, well, what is the structure of rubrene? What is this compound? Well, it's essentially a compound of fused and bonded phenyl groups. All right, and here you see just a diagram of one molecule of rubrene. However, at room temperature, it does assume the solid state, and generally the crystalline solid state, and the most general forms are in the orthorhombic crystal system, assuming the crystal class of either C2V or D2H, as you see here. Now, generally, the rubrene that you'll encounter, certainly out of the bottle, and that's often fabricated as D2H crystal class. And so that's what we'll deal with here. And here you see a schematic and this is very important, of the let's say the crystal habit with respect to the crystal axes. So kind of keep this in mind as we proceed here. Now, for a crystal in the D2H crystal class, the Raman active modes are dictated by that crystal structure, and in Rubrene there are 4 Raman active modes: AG, B1G, B2G, and B3G. These are the only Raman active modes that are in play, and these are the Raman tensors for them. And what you see then are where there are letters A, B, C, D, E, and F. Those letters indicate non-zero values for those tensor elements. All the other tensor elements are then 0. Now, why is that important? Well, when considering the Raman scattering, and here we have a simplified expression for the Raman scattering cross-section and its proportionality to, or the Raman scattering cross-section with respect to the solid angle, and its dependence then on the incident electric field in conjunction with the Raman tensor and the scattering vector. Now, what's important is that the orientation of that crystal is going to dictate how this tensor presents itself to the incident electric field and the scattering vector, which will be fixed in a micro-Raman experiment. Now, what do I mean by that? How can we understand that a little better? Well, here are 2 diagrams of Rubrene in the D2H crystal class, and they're essentially the same crystal structure, but they're just oriented differently. So you look at them and you say, my, they're really quite different. Well, no, in fact, they're the same crystal structure, but we're just looking at them along different axes. So that if you envision yourself as a laser beam heading towards this crystal of Rubrene, then depending on how it's oriented, I think you could then anticipate the different interactions of the vibrational modes and the phonons with the incident electric field. Here again, this is the same crystal structure, D2H, only at different orientations relative to your field of view or the incident beam coming at the crystal. And this last structure is going to be very important because what I've labeled here are the crystallographic axes. So this happens to be the orientation of a crystal habit that is favored in the formation or crystallization of the Rubrene. And here are 2 reflected light images of Rubrene grains taken right out of the bottle. So here's grain R1, which I've selected because it really has kind of a random orientation, whereas R3, and probably is polycrystalline, whereas R3 has a very specific crystal habit, which you can see, and we can then impose or superimpose the crystallographic axes on this habit, and then see what kind of differences we obtain in the Raman spectra obtained from these 2 grains at these locations where you see the green dot. Okay, so now we're going to look at the Raman spectra obtained from those different grains at that green dot. So the blue spectrum is the case of R3, Rubrene grain 3, in which we're looking at the C phase, and therefore our polarization, our incident polarization, was fixed in the AB plane. And the red trace is with the other grain, which for all I know is polycrystalline. And so you see the dramatic differences in the Raman spectra of these grains simply because of crystallization and orientation. All right, and these are both plotted on the same scale, same absolute scale, and spectra were collected together. Now, let's take a look at some grains, each with the reflected light images of the C face of the Rubrene grains. But notice that they're oriented 90 degrees with respect to each other. So this is another, let's say roughly single crystal with the tip broken off. And here is another single grain, or let's safely call it a single grain, and that's oriented 90 degrees with respect to this grain. So what is it that we see? And I've included the previous spectrum in the AB plane as well. If we compare these micro-Raman spectra of two grains obtained with the beam incident upon the C face, we find that for two entirely different grains, their spectra are remarkably similar, which is what we would expect based upon group theory and the Raman selection rules for crystal orientation and the polarization. And now we come to this case where, again, we're looking at a single grain, probably in the same crystal orientation, except that it's rotated 90 degrees with respect to these others. And so now we see the differences, I should say, in the relative intensities of these Raman bands, particularly at 1004 wave numbers. You look at these differences here compared to the bands at 1302, 1434, and 1524. So notice the difference now just by rotating the crystal 90 degrees with respect to these others, so that you can see how even for a single grain, the Raman spectroscopy with its incident polarized light is very sensitive to the orientation of the crystal, and not just that it's crystalline as well. So let's sum up how we can think about the use of micro-Raman spectroscopy in molecular electronics. We can think about using it with integrated electronics, photovoltaics, and displays. And why is that? Well, because the spatial scale is, and here I'm jumping ahead of myself, but that's all right, because the spatial scale of the molecular electronics is conducive to optical microspectroscopy. Your spatial resolution is well suited for the dimensions that you'll find in these organic electronics, so to speak. You have a variety of organic compounds and polymers, as well as preparative conditions that are used. So the chemistry and the solid state structure are far more complex in molecular electronics than in, say, silicon circuit fabrication. And so the value of vibrational spectroscopy of these solid state materials, I think, is very clear, because you are then able to probe and to characterize the solid state structure, for example, the crystallinity, which is so important, and its architecture needs to be controlled in order to gain the electronic performance that one needs, specifically with respect to electron and hole mobility. And let me just point out that I say this frequently, that if one can use X-ray diffraction to get the information you need about crystal structure or orientation, absolutely you should do that. What I am suggesting here is that where it is not practical to apply X-ray diffraction, particularly if you need spatial resolution or mapping out of areas to confirm relative orientations from one location to another of your crystalline materials, then polarized Raman spectroscopy, and specifically micro-Raman spectroscopy, is a very good approach to take.